So welcome back to another lecture of Powder Metallurgy MT407. So today we will be discussing on powder metal production technology. So since you are studying the subject powder metallurgy, we should understand how to make the powder possible. So almost we have found 118 elements in our periodic table. Among that, almost all material can be manufactured in the form of powder. But the choice of manufacturing technology depends upon the material specific property. So each element will be having different property. We have to make sure that it is the main criteria for choosing different methods in order to make the powder. And for that, the production of powders, we have four methods: mechanical, physical mechanical, chemical, as well as physical chemical. So the choice of manufacturing technology depends upon economic aspects. That means, for example, extraction of gold, which is a precious metal, and that is expensive. Why? Because the extractive process having different steps, and if we consider the economical aspects when compared with an iron, it is more cheaper because each process will be expensive. So we also have to consider which all process and what are the economic aspects regarding that, and the second factor in order to make sure that before going for any production method is the characteristic of the powder. For example, if the ore is present in the form of sulfides, oxides, fluorides, it's we have to rely on different methods. We have to change over with the mechanical, physical, or chemical methods. So this is the first and initial step. We'll go in details about that. So initially we will take mechanical operation first, because this method is one of the cheapest method for the production of powder, and the methods involves usually mechanical force. So we are relying on mechanical force to crush the material or the ore into final products. From this particular figure, this yellow colored rock, we can term that as an ore. A straightaway run of ore, we are taking that ore and we are crushing it. So we have different means by which we can crush that particular lumps of ore into final products. So basic idea of crushing principle is disintegrate the material. So disintegrate means we have to break the bond between the particles. So ore is normally having a greater size, we have to reduce that into a final bits. But crushing means nothing into, we can't term crushing as a final production process, because that I will explain in the later slides, but initially I will explain what this figure means. The first process is called pressure. That is, normally we are applying a force into that material. From this figure it is evident that we are giving a compression force. And the second image is called the shear force. Shear is nothing but a gliding movement or a friction type of movement where the material is being crushed. We can from the arrow shown here, we can clearly understand how the motion will be happening, and it can be termed as an shear as well as impact force, because in the figure D, it is like a mortar and pestle. Now I think you might have familiar with mortar and pestle, normally used in kitchen in order to grind or something. So we have the same motion here. So we will be ultimately getting final product. And we have wear also. Wear means we are using the power of friction to grind or just to crush the material. So I hope you might have studied in your mineral beneficiation subject. So this particular process is we can use a jaw crusher for this particular operation of crushing, where we have one fixed jaw as well as a moving jaw. There will be the motions will be like this as shown here. So the material will be crushing in between, and we will be getting finer bits of the crushed product at last. So feeding a higher bulky material, and we are getting finer grades of ores. And the first stage of a disintegration where the coarser powder is obtained. So here clearly mentioned that it's a coarser powder, not a final product, because crushing is just an initial process, and normally this is used for making ceramic materials such as oxides of metals. So that is the main application of crushing. We have size reduction equipments. So the principal types of size reduction machines are as follows. So with me, I have a scale of 30 centimeter. So you can see. So I will show regarding how the particle will be when compared with the crushers and rollers. So it is denoted that for initially we have crushers and intermediate crushers. If you look in details, what are the crushers? We have jaw crushers, gyratory crushers, cone crusher, and the crushing rolls. For this for this particular crushers, we will be having a feed size of 250 mm. That will be, for example, this scale as I mentioned, this is 30 centimeter. So 25 centimeter, that is 25 centimeter, this much. So if a particle having a size this much, you can see, I hope you can clearly see how much the particle size will be. So if the particle size will be in the ranges of 250 to 150 mm, so this is 150 and this is 250, and 150 and 250. So if a particle sizing ranging from this size, we will normally feed into crushers like jaw crushers, gyratory crushers, cone crusher. And normally after breaking down, it will be reduced into size of 50 mm. So that will be, see, 50 means this much, 50 mm, that will be the size, that is 5 centimeter. So this is the main use of coarse and fine crushers. And moving on, we have the intermediate crushers, and that can be classified into roller mill, granulator, and a hammer mill. So the further processing, we will be feeding the 50 mm particles as the feed, and we'll be getting a product of 5 mm. That is extremely small, and you can see how much will be the particle size, 0.1 mm. So normally the first process will be crushing, uses the coarse crusher unit, and then we have intermediate crusher. And moving on, we have on the third category fine crushers. So feed will be 5 to 2 mm. 5 to 2 mm will be really minute, that will be 0.05 centimeter. So that is extremely small. That kind of particles we normally feed into fine crushers, and we have the fine crushers and grinders in form of types called attrition mill, tumbling mills, and these tumbling mills can be further classified into rod mills and ball mills. We will be explaining those kind of mills in the further slides. And we have then next grade called ultra fine grinders. And why we are explaining all these stuffs, because we are dealing with powder, and our aim is to make extremely fine powder for our powder metallurgy parts. And we have ultra fine grinders where we have the feed size of 6 mm, and we are getting a product in the scale of micron. That is micron, what is the size limit? Micron, 10 raised to minus 6. That is extremely minute, and we are getting products like this. We are feeding the products in the size range below 6 mm, and we are obtaining the output in the scale of micron scale. And we have fine impact machine, fine impact mill, and those are the classification for the size reduction equipments. And for the classification of E, that is the cutting machine, and that we most probably you might be familiar with knives and scissors. So the particle size in the range of 2 to 10 mm, that is 1 centimeter. So normally we don't rely on those kind of reduction process. So what described in this particular slide is the crushing and the grinding units we normally used in this particular powder metallurgy. And I think you must be familiar with those kind of machines in your mineral beneficiation subject, because we have jaw crushers. These are small GIF animations. Jaw crushers, as I mentioned earlier, we have a fixed end and a moving end, and we are getting final product in the output. And we have a gyratory crusher where we'll be having a rotational movement, and we have attrition movement. Here the particle will be moving. This is an attrition disc kind of movement. And we have ball mill, one of the most commonly used grinding operation. And we have roll crushers where higher feed will be adding at the top, and we are getting finer feed in the bottom. And we have planetary crushers where you can clearly observe how the movement is happening, the particle movement is happening. Normally two kind of movement is happening in planetary crusher. We will be going into detail in the further slides. But from this GIF we can understand how the motions are normally happened in most of the process. So these are the most common methods we are dealing in powder metallurgy, and we will be studying in detail about this process in the coming slide. So going into details, ball milling process. So we have a cylindrical vessel rotating. From this figure, this is an animation GIF where we have a rotational movement, and the red balls are our hardened material. That is, the vessel is charged with grinding mediums. So these red particles, red balls are the grinding medium. So normally this material is hardened steel or tungsten carbide, which is the strongest material, and a ceramic like agate, porcelain, aluminum, and zirconium. So agate is this kind of material. It seems like a pebble-like structure. Normally we used for grinding. You might have seen in most of the manufacturing process. It's a common material, and we have porcelain balls. And for initially, what I included in this particular figure is a titanium sponge iron. That is normally in order to manufacturing titanium, we go for sponge titanium, and that material had to be grinded. That process we go for ball milling, and we have shown here is the we have shown a tungsten carbide ball, and this is a hardest material, and whenever we incorporate this kind of material into the ball milling, we will be ultimately getting very fine particles. And this is the basic idea about ball milling, and the reason and the real mechanism behind how this particle is getting reduced is that impact, collision, and attrition that we already have seen in the mechanical process. The impact force, the collision force, and the attrition will be the governing factor for this ball milling operation. So we are going step by step process. As I mentioned earlier, this is the ball mill. This is the ball mill process. We have a rotational movement here. Inside we have particles, balls, in which the feed is added, and due to attrition and collision, the particle is being reduced into finer bits. And we have certain properties and certain principles for this ball milling. For example, the armor material, this because the brown color material you are seeing is made up of manganese alloy steel. That is manganese alloy steel, which is a hardened material, and we are building this particular ball milling equipment. All this machine is all built upon manganese steel. Okay, manganese alloy steel. And for example, and next is the ball material. You might have seen the ball rotating in the previous slide in the red color ball. So that ball is normally made of manganese steel, same with the chromium steel alloy, that is chrome steel alloy. So they are normally hard material, hardened alloyed steel, so which have a very tough property or tough resistance, or wear resistant property. That's why we are using those kind of material in ball mill. So now there is a comparison. If the drum length is equal to 1.5 into drum diameter, or drum length is less than 1.5 into drum diameter, we normally call those kind of ball mills are called tube mills. So we have a comparison of ball mill. Even the ball mill can be classified into different types, as I mentioned in the previous slide. So this comparison is on basis of the drum length and the drum diameter. From this equation, clearly understand how to classify a ball mill according to its length and the diameter. How we classify into tube mill, and this is the explanation. And next, if you remove the steel balls and replace it with the hard pebbles, for example, clearly I mentioned what kind of balls we are using. It's a round titanium carbide or different kind of material balls. Replacing this ball with pebbles, we have another kind of ball mill operation. So as mentioned earlier, if you replace the ball mill with pebbles, we have a pebble mill, and same with if you remove the balls, replace it with steel rods, we have a rod mill. So next is an explanation about what is this rod mill is actually about. So we have a horizontal rod and used instead of ball to grind. So this has been practiced from the early ages.
These machines are called rod mills. So revolving cylinders 12 feet long, 6 feet in diameter.
So you can watch
round and round, 10 of them breaking the ore to pieces smaller than a grain of wheat.
Mill speeds vary from
Here's what's going on inside.
So
35,000 pounds of steel rods, hammering against 28,000
rotating.
pounds of manganese steel plates, whirling around 17 times a minute. Tough going for the ore and for the steel rods too. This is what a 10-foot rod looks like after going through the mill. In the rod mill, much of the ore is ground fine enough and requires no further grinding. And this machine, called a classifier, floats the fine ore out and sends it on its way.
And thus we have the rod process, rod milling operations. So this is also a classification of ball milling operation. And in milling operation also we have the further classification on the basis of dry and wet milling. And in dry milling, from the name itself, 20% of volume of the powder is added along with 1 weight percentage of lubricants. So these lubricants are normally acids. So we have in our case stearic acid and oleic acid. So this is the process where dry milling is happening. And there are some of the minerals or metals we incorporate this kind of dry milling operations, but I am not going into deep into the mineral beneficiation operations, but this is a comparison. And we have the wet milling operation where 30% is compared with dry milling. We are taking more volume of powder, and we are adding 1% of dispersing agents such as water. And here you can see that how the slurry is made. That is in the case of wet milling operation, we have the slurry, and here it is clearly shown 3 parts is solid and 1 part is water. So that is the wet milling operation. And we have the optimum speed for that roller. I'm sorry for the technical issues we are facing now. And the optimum speed for this particular ball milling will be the 75% of the critical speed. So what do you mean by critical speed? So this critical speed is nothing but it is a definition of a centrifugal force equal to the force of gravity. So we have the rotational moment, and that means the centrifugal force is happening, and this is making the particle to rotate. So we approach to the last operation, our mechanical operation, that is the attrition mill. So we have the process. The feed is grounded to fine size by the action of vertical shaft with the side arms. From this video it is clearly understandable, like we have a shaft here and it has certain side arms, and we are enhancing the particle to be finely crushed or grinded into final particle. So this method is more efficient in achieving fine particle size. So these are the references I used for making this particular lecture, and I also used a couple of images from the textbooks. I'm sorry for the technical issues we have faced today, and we will be rectifying in the coming future and the coming lectures. And thank you. I'm looking forward to meet you in the next class. Thank you.